So today we will start our new chapter, that is bond and types of bond. Okay. So what is bond? Bond is defined as the addition between concrete and steel which resist the slipping of steel bars from concrete. Types are encourage bond or development length or flexural bond. Next is bond stress. The stress generated due to a bond between concrete and steel is called bond stress. So for various concrete grade, various bond stress value is given. We can designate the bond stress at tau BD. For M20 this is 1.2, for M25 this is 1.4, similarly for M35, M30, M35 and M40 it goes to 1.9. These values are given in IS 456. Okay, for concrete, for which concrete grade, what is the value of tau VD? Again, next point, for deformed bars, the tau VD will increase by 60%, and for bars in compression, the value of tau VD should be increased by 25% as compared to tension. So for deformed bars, the tau VD is increased by 60%. For bars in compression, it is increased by 25% as compared to tension. Next we will discuss something about development length. You can see here a beam with the reinforcement bar embedded into it. Concrete section, this is the concrete section. The reinforcement bar is there. You can see here, this is embedded up to which length? To this much length. So this is called our development length, and here bond stress is acting between surface of concrete and reinforcement bar. So this is the tensile force. Okay, so when it will slip, when this tensile force is greater than the force generated due to bond stress. Okay, so to avoid slipping, the tensile force should be less than the force generated due to bond stress. Okay, so that is T should be less than tau VD into 2 pi into 5 by 2 into LD. So T is equal to our, okay, this is one condition. For no slipping, to avoid slipping, T should be less than this much value. But in other words, T is our, this is tensile, this is tensile stress, similar, this is tensile stress, this is tensile force. So sigma st into pi by 4 phi square, this area, this cross section area, this cross section area. Okay, so these two values are same, as both represent our T. So sigma st into pi by 4 phi square is equal to tau VD into 2 pi 5 by 2 LD. So from this we will get LD development like this, phi into sigma st divided by 4 tau VD. Okay, here sigma st is nothing but our 0.87 Fy. Okay, so our development length is 0.87 Fy, 4 tau VD. Fy is yield stress, phi is the diameter of the bar, tau VD is the bond stress. Okay, so as discussed, for deformed bars, the tau VD value is increased by 60%, and for bars in tension it is increased by, and for bars in compression it is increased by 25%, and bars in tension it remain unchanged. Okay, next is anchorage values for hooks, 90-degree bend and 45-degree bend of standard lapping of bars. You can see here for bars in tension, for 90-degree, you can see this is the diameter of the bar, this is 5, from this to this is 4 phi. Okay, and this radius is k phi, and this distance is k plus 1 phi. For standard hook, this is 90-degree bar, and this is our standard hook. This is 4 5, this is k5, and this is k plus 1 5. So minimum value of k is 2 for mild steel. From cold work steel this is 4. So these are some conditions for bars in tension. Deformed bars may not need encourage. Hooks should be provided for plain bar in tension. The encourage value of standard bend shall be considered 4 times the diameter of the bar for each 45-degree bar bend. Okay, subjected to maximum value of 16 times the diameter of the bar. The encourage value of standard U-type hook bar shall be 16 times the diameter of the bar. Okay, the encourage value, this is 16 times the diameter of the bar, L0. Okay, next, for bars in tension, bars in compression, the encourage length, that is L0 of straight compression bar shall be equal to a development length of straight compression bar. Okay, next, the development length shall include the projected length of hooks, bends, and straight length beyond bends. Again, bars in shear. Inclined bars in tension zone will have the LD equal to the bars of bars in tension, and this length shall be measured from the end of the inclined portion of the bar. Inclined bars in compression zone will have the LD equal to the bars in tension, and this length shall be measured from the middle depth of the beam. For stirrups, transfer ties, and other secondary reinforcement, complete LD and encourage are considered to be satisfied if prepared as like this. So for 45-degree bars, you can see L0 is 4 5. For 90-degree, this is 8 5. For U, this is 16 5. So 3 types: 4 5, 8 5, 16 5. For this is 45-degree, 90-degree, and for this is 180-degree. All are the values of L0, that is encourage length. So for any development length problem, our M1 by V plus L0 should be greater than or equal to LD. M1 is the moment of resistance, V is the shear force, L0 is the, what is L0? L0 is the encourage length, should be greater than or equal to development length. If this does not satisfy, then we have to increase encourage length and reduce the number of bent top bars. Okay, this condition should be satisfied. Okay, where M1 is the moment of resistance that I have already told you, V is the shear force at this section, and U is the encourage length. Okay, so M1 by V can be increased by 30%. That should be 1.3 M1V when end of the reinforcement are confined by compression reaction. Okay. Next, our problem is an RCC beam of 250. This is 250. Depth is 500. Is a clear span of 5.5 meter. This is 5.5 meter. The beam has 220 mm diameter bar. This is 220 mm diameter bar going into the support. View is 140. Check the LD if F415 and M20 is used. So for if total overall depth is 500, then effective depth is 470. This is clear cover, and this is half of the diameter of the reinforcing bar. L is 5.5. AST at the support is 2, as there is 2 numbers of bars, so we should multiply 2 into pi by 4 of d square. This is 628. Q is given in the question. This is 140 kilonewton. So as per IS 456 codal provision, M1 is equal to 0.87 Fy AST into T into 1 minus AST Fy by BD FCK. So the value is 94.748 into 10 to the power 6 Newton mm. So M1 value is 94.748 into 10 to the power 6 Newton mm. Now, as we got M1, we know B, we know L0. So we have to check that codal provision M1 by B plus L0 should be greater than equal to LD. So LD is 0.8755 for tau VD. So tau VD value is 1.6 into 1.2. Because for deformed bars it is increased by 60%. Okay. So tau VD is for M20 tau VD is 1.2. For deformed bars it is increased by 60%. So this becomes 1.92 Newton per mm square. The development length is 940.2 mm. So provided we know M1, we know B, we know LD. So provided 90-degree bend at center of the support. Provide a 90-degree bend at the center of the support. Suppose this is our column, this is our beam. So 90-degree bend in the center of the support. For 90-degree bend, L0 is 85. So M1 by V plus L0, the value is 836. But this is less than LD, but it should be greater than LD. So provide a U bend at the end of the bar. So U bend, when we provide U bend, this value becomes M1 by B plus L0 becomes 997, that is greater than LD, as our LD value is 940.2. When we take U bend bar, this is okay, but when we take 90-degree bend of bar, 90 degree, that becomes M1 by V plus L0 becomes less than LD, that is wrong. So we have to take a U bend bar, so this becomes greater than LD, so that is okay. Now check the diagram. Okay, this is LD, but this is 90-degree bend of bar, so we have to provide a U bar. Okay, so the figure will be like this. Okay, with this development length chapter is over. So what is the procedure to solve a problem? So first, from the given data, we have to find out the moment of resistance. From that moment of resistance and the given value of shear force, we have to, and from given data, other data, we have to find out LD, development length. We have to assume a bend, we have to provide a bend and check whether M1 by V plus L0 is greater than or not with the LD. If that is not greater, then we have to change the bend style. If we have provide 90 degree, we have to provide U bend and again check it. If that satisfied, that is okay. And as per that condition, we have to provide our bending in the design process. Okay, thank you.